The generation of physicists that would remake the model of the atom were, by and large, impossibly young. With the exception of Erwin Schrödinger, the students of the men who had established the quantum nature of the atom were in their early 20s when they began to reconsider that model with its orbitals and energy levels. What none of them expected, at least at first, is that they would end up not only redefining the atom, but altering the way in which we understand the very nature of matter. Kramers, Pauli, Heisenberg, Jordan, and Dirac wouldn't just remake physics, but they would do it, by and large, by the age when most contemporary physics students are just finishing their undergraduate education. In doing so, they would establish the expectation that if a student hasn't done something truly paradigm-altering by their 25th birthday, they never will. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 15, The Mechanical Atom, Part 1. When last we left our story, Niels Bohr, Arnold Sommerfeld, Max Born, and to a lesser degree Paul Ehrenfest were struggling with what is now called the old quantum model of the atom. The model had great success in some regards, but failed in others. To address these shortcomings, these scientists had established a research program in the great universities of Central Europe, in Munich, Göttingen, and Berlin in Germany, Leiden in Holland, Zurich in Switzerland, and of course, Copenhagen in Denmark. The program was excellent as one in which communication between the scientists was frequent, and the problems being assigned to the students were fairly easy, clear, manageable, and tractable using the methods of physics that had been developed over the previous century. In addition, there were lots of good experimental data to compare the theoretical results to in order to evaluate the efficacy of the work in moving the overall program forward. So, if the program was so strong, and to be clear here, it really was, why was there this growing sense of crisis as mentioned in the biographies and memoirs of almost every single person who participated in it? As I've already mentioned, there was a problem of the results of the work not matching up with the data as precisely as hoped in many cases. But really, there was something much deeper going on here. Now, as a bibliographic note, much of my commentary on this is adapted from the lecture notes of Catherine Carson, whose class on the history of modern physics at the University of California at Berkeley can be found on iTunes U. The much deeper problem here was that the model was really only what I might call semi-classical, or, as one reads in the literature, semi-quantum, to use a more forward-looking term. The model's foundation was really in classical physics ideas, with quantum modifications being made as necessary, something that had started with Planck. While this is entirely understandable in the framework of the traditional process of hypothesis modification, it was something that was applied on a somewhat ad hoc basis. The quantization of quantities and the application of the results of this approach were guided only by the imperative that the theoretical work produce predictions that match the empirical data. There wasn't a good sense of exactly when to use classical methods, when to use quantum methods, or when to use both in a particular problem, or, more importantly, why one would choose a particular way of doing things. This led to a growing realization among the participants that the methods of making small corrections would never actually resolve the fundamental areas of disagreement. As a historical note, the report of the deepening dissatisfaction among the participants of the program as a crisis, that's the word that's used over and over again, almost certainly has its roots in the run-in up to World War I. While a majority of the participants were too young to have been involved in the fighting in the war, they were students of the causes of the conflict and they saw parallels in the growing difficulty of the methods to solve the problems they were considering to the series of impasses that grew in frequency and intensity in the years leading up to the war. Just as various conflicts of territory and empire had escalated following the revolutions of 1848 and the Franco-Prussian War in 1870, there was this idea of a fundamental ineffectiveness of the old European imperial system to deal with the new challenges of nationalism and arms escalation. In the same way, there was a sense in the halls of the physics institutes around Austria, Germany, and Denmark in the early 1920s that the increasingly patchwork nature of the model was losing its ability to address the problems being considered in a realistic way. With the benefit of hindsight, we, of course, now know that this was resolved with a revolution that, as Werner Heisenberg, one of its chief architects, said, changed as little as possible. But that, in fact, ended up changing just about everything. However, as I mentioned in the last episode, it would be a mistake to accept the narrative that suggests that it was solely this research program that was responsible for the overturning of the old model and picture. Instead, it was in a place scientifically far from this nucleus of research that showed the first hints of how to think about matter and particles of it that would offer a way to resolve the problems with the Bohr-Sommerfeld model. The man who would first spark this was the son of a French prince, and his name was Louis. Louis Victor Pierre Ramon was born in 1892 as the son of the 5th Duc de Broglie. He had originally planned to study humanities in college, initially earning a degree in history, before switching to mathematics and physics. In the Great War, he had served France by working on projects devoted to developing radio communications. At the end of the war, he returned to his study in physics, and his project was initially looking at the quantum ideas of Planck and Einstein as they applied to light. Especially intriguing to him was Einstein's assertion about the dual nature of light, that it had properties of both particles and waves depending on how you made the measurements of the phenomenon. Louis began to wonder why the same thing couldn't be said about the electron. Consider light, he thought. Newton had shown that it was a particle. Young had shown it to be a wave. Maxwell had derived a mathematical description of light as a wave. Planck and Einstein had treated light as a particle with wave properties in order to solve problems otherwise intractable, developing a particle-based mathematical description to go along with that of Maxwell. When Thomson had discovered the electron, de Broglie realized that the detection methods Thomson used were predisposed to detect particles, and so that's what Thomson had observed. But what if there were a way to look for electrons not as particles, but as waves? If that were done, de Broglie guessed that the electron would be shown to have wave properties as well. So how could he show that to be true? As de Broglie didn't have the means to directly test this hypothesis, he did realize that assuming the electrons were a wave would have consequences for the Bohr-Sommerfeld model of the atom. So what he did was work out what it would mean for a wave-like electron to orbit a simple nucleus. What he showed was that by assuming the electron was a wave, he could mathematically derive the energy levels of the Bohr model of the hydrogen atom as the specific orbits where the wave function of the electron would reinforce itself. So what exactly does that mean? Well, that can be hard to explain, but we'll give it a try. Imagine that you have a rope with one end attached to a pole, and you get to hold the other end. If you start moving your hand up and down on the rope, you'll send a wave along the rope. When the wave gets to the pole, it will be reflected back towards you. Now, that reflected wave will interact with the next wave you send down the rope. If the conditions are right, the interactions will amplify the second wave. If not, the reflected wave will cancel it out. The former is called constructive interference, while the latter is known as destructive interference. This will happen with each wave you send down the rope. Now, if you send waves down the rope at regular intervals, you'll have both the waves you send and the reflected waves interacting all along the rope. It turns out that if you send the repeated waves down the rope with very specific frequencies, they will interact with the reflected waves in such a way that there will be constructive interference everywhere along the rope. This will lead to what is known as a standing wave, where the wave pattern looks like it is sitting still on the rope, moving up and down in specific unchanging places and standing still in other unchanging places. For the lowest frequency, the ends of the rope will stand still, and the middle of the rope will move up and down with the greatest amplitude. If you double the frequency of the wave you send down the rope, a standing wave will be established where not only are the ends of the rope stationary, but so is a point halfway between them. The rope will oscillate with a maximum amplitude at the points that are halfway between an end and that center node, as it is called. Now, if you try to wiggle the rope with a frequency that is between the two standing wave frequencies, all you'll get is some uncoordinated motion along the rope that doesn't look like much. For each integer multiple of the original frequency, you'll get a standing wave in the rope with an additional node, but only at those very specific frequencies. What de Broglie said was that if an electron can act like a wave that orbits the nucleus, it has the ability to reinforce its own wave pattern if the size of the orbit is just right. If the orbit was too big or too small, the wave wouldn't reinforce itself, and so the electron was said not to be able to orbit there. From this assumption, he was able to derive the specific energy levels of the simple Bohr atoms, thus offering a good bit of guidance as to where the quantum approaches should be used in dealing with the various quantities possessed associated with the electron. While it didn't solve everything, de Broglie's suggestion that electrons, and probably other subatomic particles as well, displayed wave behavior really shook up the world of physics. When he submitted his thesis in 1924 with this idea, his dissertation committee was at a loss how to treat it. Only when the work was shown to Einstein, who was enthusiastic about the direction it took, did the committee award de Broglie his PhD. Once the wave nature of electrons was observed in 1927, it wasn't long before the French nobleman was awarded the Nobel Prize, something that occurred in 1929. At this point, the focus on the atom is still centered around working with things that are fundamentally classical, namely the orbit through space of the electron. While de Broglie is working to reconsider what these orbits might represent, the group around Bohr was taking a significantly different track. In order to try to salvage the model, Bohr, along with two very young postdoctoral students, the Dutch physicist Hans Kramer and the American John Slater, put forward the idea that on the scale of the very small, energy and momentum weren't actually conserved on an individual particle basis. Rather, they suggested that these quantities would only be conserved in a statistical sense when larger numbers of such interactions would take place. Now, we talked about momentum briefly in the last episode, and the idea that the momentum of a closed system was a quantity that couldn't be changed dated all the way back to the work of Newton as an outgrowth of his second law of motion. While the idea of energy couldn't be created or destroyed, just changed in form, went back only as far as the 19th century work in thermodynamics, it had been shown to be the most powerful tool in the formidable arsenal of the physicist when treating difficult problems. To suggest that when a photon of light interacted with an electron, these two quantities didn't have to obey the same physical laws that macroscopic objects did was a bold departure from the norm. Actually, it was the exact kind of thing Karl Popper would have applauded just a few years after this as an example of a revolutionary new hypothesis that made bold and falsifiable predictions of the sort that could be tested. That's a topic we'll come back to in a later podcast. Within a year of the BKS paper, named for the first letters of the last names of the authors, Hans Geiger and Walther Botha were able to show that the interaction between a photon of light and an electron did, in fact, conserve both momentum and energy, thus spectacularly disproving Bohr's idea. While disappointed with the outcome, Bohr was good-natured about it, famously saying, There is nothing else to do but give our revolutionary efforts as honorable a funeral as possible. The paper was, however, deeply influential on a number of people, most notably the young and brilliant Werner Heisenberg and his postdoctoral advisor, Max Born. Heisenberg was one of the students being brought up in the program we discussed at the beginning of the episode. He was very good at solving well-defined sorts of problems students were given and worked quickly through the standard curriculum, earning his PhD at the stunningly early age of 22 in the year 1923 after working on problems in turbulence. In the year before receiving his PhD, Heisenberg had attended the 1922 lectures of Niels Bohr as a student of Sommerfeld and was completely captivated not only by the subject, but also by Bohr's novel approach to considering physical problems. Following his postdoc with Born, Heisenberg received a Rockefeller Fellowship to study with Bohr in Copenhagen. While there, he got to see the genesis of the BKS theory as well as its refutation. He was also introduced to another young prodigy, Wolfgang Pauli. Now, in that year, the same year of the BKS paper, 1924, Pauli had published his paper on the exclusion principle, something we talked about in the last episode, and in doing so, had established himself as one of the most brilliant mathematical thinkers in theoretical physics. Actually, he had sort of already done that in writing a review article of Einstein's theory of special relativity as a high school student that was so brilliant that it captivated the physical minds throughout Europe. Now, Heisenberg had followed Pauli's educational path from Sommerfeld to Born, and so it was natural that once Heisenberg had completed his education, the two would become more closely acquainted. One of the defining characteristics of Pauli's work and thinking was his focus on what were thought of as observable quantities. While I'd like to save the broader discussion of the philosophical trends through the development of atomic theory to an interlude series that will follow our history of the atom, a few words here might be in order. Pauli was literally the godson of the physicist Ernst Mach, and was baptized, if such a term can be properly used in this context, into an anti-metaphysical philosophy by Mach, who was, by the way, a colleague of Pauli's father. Following from Mach's tempered positivist roots, Pauli thought that the work of physics should focus only on those quantities that were observable by the senses. This led Pauli to be somewhat critical of the Bohr model and its focus on electron orbitals. As these orbitals could not be observed, Pauli questioned whether they were things that any sort of theory should be built around. In a 1924 paper, in fact, Pauli removed all mention of electron orbits, telling Bohr that he felt that the energy and momentum of an electron, as measurable quantities, were more real than the unobservable electron orbits. Interestingly, this was as far as Pauli would be able to make himself go. He just couldn't get himself to truly commit to a non-classical view of what was going on in the atom. Even if he could do away with the parts no one could observe. Later in his life about this kind of thing, Pauli would write, quote, "When I was young, I thought I was the best formalist of my time. I thought I was the revolutionary. When the big problems would come, I would be the one who would solve them and write about them. The big problems came, passed by. Others solved them and wrote about them. I was the classicist and not the revolutionary." Unquote. So who were the revolutionaries? The first to show himself able to let go of the classical view of the atom was Werner Heisenberg, and thus it is he who is considered by historians as the real innovator from the program we've been discussing. Heisenberg was the one who was willing to take the risks needed to find the path to the answer, though, as we'll see, he was not without his misgivings. As Heisenberg witnessed the last, best attempt to salvage the Bohr-Sommerfeld model fail, he was engulfed by the sense of crisis that overtook all of those working on the project. He had been working on a model to explain electron transitions, but quickly realized that it, too, was making the use of completely unobservable mechanisms to try and make things work out. The way the story goes, Heisenberg had already rejected the idea of electron orbits in late 1924 just before he went to work at Copenhagen. While working with Bohr and Kramers, he began to fiddle with the solution to the problem of electron transitions and the resulting spectra that tried not to make use of orbits, but instead focused on treating the electron as a type of oscillator. Here again, let me note, the subject matter is about to move into a realm where it's very difficult to explain the ideas without a strong mathematical framework that goes well beyond the scope of this podcast. As such, I will mostly be giving very general descriptions of the work, and then relaying the results with an attempt to interpret them. This may leave some of you feeling a bit dissatisfied, as I won't be giving you a really clear enunciation of the path someone like Heisenberg took to get to their conclusions. While I apologize for this lack of clarity, the only way I can see getting around it is to have you all take about 2 years of calculus and a year and a half of college-level physics before we can really do what these guys did. And if you've got that kind of preparation, you probably already know what I'm going to say from the science side anyways. Thus, I'll try to steer us towards a historical development and the work from there. Okay, with that caveat, let's get back to the story. When Heisenberg finished up in Copenhagen, he returned to Göttingen to resume his lecturer duties there. Unfortunately, he suffered from hay fever and had a pretty extreme attack of it during the summer of 1925. The only remedy for him was to travel to the island of Helgoland in the North Sea, a fairly barren place lacking in both vegetation and distractions. Taking only a few things for a short visit, he planned only to stay long enough to have his hay fever clear up and to get his body to recover. Among the items were his well-worn hiking boots, a copy of some poetry of Goethe's, and some calculations on the electron oscillator he'd been working on in Copenhagen that had continued to give him trouble. The oscillator was a nice little problem to work on, because it seemed like it would be a whole lot simpler than what might be going on in a real atom. What Heisenberg had been trying to do was explain how treating the electron like a particle on the end of a spring moving back and forth would affect the electron's interaction with light without having to explicitly describe its path in space. Remember, that was one of those things that Pauli had said was unobservable. Heisenberg's hope was that if he could figure out how to describe the system without having to explicitly know the electron's path through space as it oscillated, he would be able to make progress using the same methods with an electron in an atom. What he was stuck on was trying to calculate the relationship between the electron's position and its momentum. In the classical physics described by Newton, if you multiplied the two quantities together for an object, it didn't matter what order you did that in. Multiplying the position of an object by its momentum gave you the same number as multiplying the momentum by the position. The operation, as it is called, is known as being commutative. You may remember this from an algebra class you've taken in the past. A times B equals B times A. Heisenberg was trying to understand how these quantities changed when the oscillator underwent transitions from one discrete energy state to another. He was able to work on the problem with some success, first by treating the oscillator as having virtual states, and then by redoing the problem by using a different method called perturbation theory. Both methods gave consistent results, but relied on unobservable quantities. This, though, gave Heisenberg confidence that there was an underlying consistent set of physical principles at work. With this belief, Heisenberg attacked the oscillator problem using a method that didn't rely on unobservable quantities, but that replaced them with the probabilities that the electron would transition from one energy level to the next. This approach required that Heisenberg represent the position and momentum of the electron as matrices. So what's a matrix? In mathematical term, it's an expansion of the concept of what a number is, in that it is an array of numbers that are associated with each other. The numbers are laid out in a table of sorts that can be multiplied by other tables of numbers using very specific sets of rules we call linear algebra. Now, while regular numbers, what we sometimes call scalars, obey the commutative property or rule of multiplication, matrices don't have to do that. While the multiplication of matrix A times matrix B might equal the multiplication of matrix B times matrix A, Oftentimes, that isn't what happens. What Heisenberg found after one very long night of intense calculation was that the product of the position times the momentum of an electron in his system was not equal to the product of the momentum times the position. The two products actually differed by the quantity of the square root of -1, sometimes called I, times Planck's constant, divided by 2 pi, something that was now understood to indicate quantum behavior in a system. As Heisenberg wrote of his discovery, quote, "There was a moment in Helgoland in which the inspiration came to me. It was rather late at night. I laboriously did the calculations and they checked. I went out to lie on a rock looking out at the sea, saw the sunrise, and was happy." Unquote. Now this story sounds like one of those cases where the lone scientist, working in a monastic setting all by him or herself, develops a revolutionary breakthrough that fundamentally alters how everybody sees everything. Such a picture, at least in my mind, is pretty limited. While Heisenberg certainly had the leap of intuition that led to his discovery, and he did that on his own, we know that during this period he was in frequent communication with both Wolfgang Pauli and Max Born, even while he was on Helgoland. Additionally, without that year spent in Copenhagen and the work he did with Bohr's student, Kramers, he would likely not have gotten to the point where he was able to make such a leap. However, even with these qualifications, it is clear that Heisenberg had made a revolutionary break with the semi-classical picture of the atom, and had shown a way to consider the electron without having to resort to classical orbit theory. If the approach could be successfully applied to a real atom, as opposed to the toy problem of the electron oscillator, it would go a very long ways towards resolving the state of crisis atomic physics was in at that point. Returning to the mainland, Heisenberg first visited Pauli to show him the results. Pauli's reaction was generally favorable, and thus Heisenberg set to preparing a paper for publication. Worried that his results, so radical in their implications, contained an error, he gave a draft of the manuscript to Pauli to review. He also sent a second copy of the draft to Born, who, as Göttingen's senior theorist, would be able to offer a strong critique of the paper from someone in the old guard of physics. Heisenberg asked him to send the paper off for publication if he thought everything was in order, while he went to give a series of lectures. Born set the paper aside for a few days in order to attend to some other matters, but when he picked it up and read it, he was dumbfounded by the work he found therein. Not only was the work groundbreaking, it reminded Bohr of something he had seen before. As he wrote later, quote, "I began to ponder about his symbolic multiplication, and was soon so involved in it that I thought the whole day and could barely sleep at night. For I felt that there was something fundamental behind it. And one morning, I suddenly saw the light. Heisenberg's symbolic multiplication was nothing but matrix calculation well known to me since my student days." Unquote. Heisenberg was a physicist rather than a mathematician, and as such, he was only familiar with the math generally used in his field rather than the much broader set of tools mathematicians had developed for their own use. Born had studied this particular branch of mathematics, what we now call linear algebra, and understood that Heisenberg had essentially reinvented it in order to do his work. What this meant was that there were actually a whole slew of tools that could be used to check and extend Heisenberg's ideas that didn't actually have to be rediscovered. After submitting Heisenberg's manuscript for publication, Born and another student, Pascual Jordan, prepared a second paper, formalizing and extending the work using the matrix methods, and when Heisenberg returned from giving a series of lectures at Cambridge, the three collaborated on a third paper. These three papers, published in the second half of 1925, set the foundations of what was to become known as the matrix mechanics formulation of quantum theory. Shortly after this, in early 1926, Pauli used the Heisenberg matrix mechanics method to derive the emission spectrum of the hydrogen atom. While the calculations were much longer and more tedious than the method Bohr had used 13 years earlier to arrive at basically the same results, they were not burdened with the ad hoc assumption of Bohr's model, and they were also easily extendable to solving the problems related to the Zeeman effect. In that same year, a 23-year-old British theoretical physicist working for Rutherford at Cambridge, Paul Dirac, was able to derive Heisenberg's relationship independently from a different line of reasoning. These two results thus established the relationship's validity and set quantum mechanics off on a new path. The new theory had many contributors: Pauli, Dirac, Born, and Jourdain. But it had been Heisenberg who had sparked off the revolution through his willingness to let go of the classical idea that position and momentum were commutative, and thus he was able to establish the quantum nature of the electron. What Heisenberg hadn't yet realized, however, was the true nature of the revolution he had started. It was one that would take 2 more years to fully understand and appreciate. In this time, there would be another revolutionary figure, one from outside the program, who would take up the ideas of de Broglie and offer a different method of looking at the electron in its motion around the atom. The work of Erwin Schrödinger would disrupt the emerging clarity of the quantum theory in such a way that a showdown would take place at the 1927 Solvay Conference that would bring the fullness of the revolution that was now underway to fruition. As I wrap up this week's edition of the podcast, I want to remind you that you can interact with the show in several different ways. Write a review on iTunes or Stitcher, leave a comment or a question on the website, thescientificodyssey.typepad.com, or join the discussion at our Facebook page. I'd especially love to hear your thoughts and questions ahead of our upcoming Odds, Ends, and Questions podcast that will conclude this series in just a couple of weeks. Following that, we'll take the philosophical interlude I mentioned earlier in this podcast in order to get a better sense of what all this might mean. Before that, though, we have to get through our discussion of the mathematical atom. So until next time, full sails on your journey.